This week, NASA made it official. A galaxy called MOM-Z14 has just been peer-reviewed and confirmed as the most distant object humanity has ever detected. Its light emitted only 280 million years after the Big Bang, traveling for over 13 billion years to reach the lens of the James Webb Space Telescope. Rohan Naidu, the MIT astrophysicist who led the study, put it plainly in the NASA statement. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting. This record will probably be broken again. Webb breaks its own records the way the rest of us break promises, regularly and without much warning. But here's what won't change: what this galaxy and dozens like it are telling us about the Big Bang itself. Because what Webb keeps finding out there isn't just surprising, it's wrong. Wrong in ways our best models never anticipated, and wrong in ways we can't simply look away from. Before we go any further, let's establish exactly how serious this is, because this isn't fringe science, and it isn't headlines chasing clicks. These are peer-reviewed numbers, and they don't leave much room for comfort. First, the universe is estimated to be 13.8 billion years old. MOM-Z14 emitted its light just 280 million years into that timeline. That means Webb is now observing the universe when it was barely 2% of its current age. We are looking at cosmic infancy, not childhood, not adolescence. Infancy. Second, Webb isn't just finding a few unexpected galaxies at that depth. It is finding them at a rate roughly 100 to 200 times higher than our theoretical models predicted they should exist. Not twice as many, not 10 times as many, 100 to 200 times. Third, there is a direct, irreconcilable conflict between the two most precise measurements we have of how fast the universe is expanding. That conflict, called the Hubble tension, has now exceeded 5 sigma statistical significance. In science, 5 sigma is the threshold for a confirmed discovery. What it means here is that the odds of this disagreement being a simple measurement error are, for all practical purposes, 0. 3 numbers. 1 conclusion: something is wrong with the model. To understand why what Webb is finding matters so much, you need to understand what we thought we already knew, and how confident we were that we knew it. The Big Bang model has been the foundation of modern cosmology for nearly a century. It tells us the universe began approximately 13.8 billion years ago from an unimaginably dense, hot point, and has been expanding and cooling ever since. Built on top of that foundation is a more specific framework called lambda cold dark matter, or lambda CDM. This is the standard model of cosmology, the complete theoretical picture of how the universe evolved from that first moment into the vast, structured cosmos we observe today. It has been tested against decades of observation. It has survived every major instrument humanity has pointed at the sky, and it makes very specific predictions about how galaxies form. According to lambda CDM, galaxy formation is slow, hierarchical, patient. Tiny clouds of gas and dark matter collapse under gravity, forming the first small structures. Those structures merge, then merge again. Over hundreds of millions of years, sometimes billions, they gradually assemble into the large, complex galaxies we see in the mature universe. The model doesn't just suggest this process, it requires it. It builds the entire architecture of cosmic structure on this slow, bottom-up assembly. Before 2022, the observational record supported this picture reasonably well. In the entire first 500 million years of cosmic history, astronomers had confirmed exactly one galaxy, GN-Z11, detected by the Hubble Space Telescope. 1 in 500 million years of universe. That fit. That made sense within the model's predictions. Then came Webb. The James Webb Space Telescope launched in December 2021. It cost $10 billion, took 30 years to build, and represents the combined effort of more than 300 universities, organizations, and 17 countries across the globe. Its revolutionary design is tuned specifically to infrared light, which matters enormously because the expansion of space stretches the visible light emitted by the earliest galaxies into the infrared spectrum by the time it reaches us. Hubble couldn't see it. Webb was built for exactly this. It was the instrument the field had been waiting for. Scientists expected Webb to confirm lambda CDM, to fill in details, to sharpen the picture they already had. They were ready for refinement. They were not ready for what the data actually showed. The first public science data from Webb dropped in 2022. Within weeks, not months, not years, the alarm bells started ringing. Astronomer Ivo Labbé and his colleagues were analyzing Webb's early infrared imaging when they identified 6 candidate galaxies sitting at redshifts between Z equals 7 and Z equals 10. In cosmological terms, that places them between 500 and 800 million years after the Big Bang. Deep in the era, lambda CDM describes as the universe's slow, tentative adolescence, when large structures were still supposedly assembling themselves piece by piece. The problem was the size of these galaxies. Their inferred stellar masses were enormous, preposterously, almost impossibly enormous, and the paper Labbé's team published in Nature sent a quiet tremor through the entire field. Mike Boylan-Colchin heard it. The University of Texas astrophysicist looked at those mass estimates and did what physicists do. He ran the numbers. What he found didn't just challenge the model, it threatened something more fundamental than any theoretical framework. It threatened the basic matter budget of the early universe itself. Stop and sit with that for a second. The universe contains a finite amount of ordinary matter, atoms, the building blocks of everything that has ever existed. In the early universe, that reservoir was fixed. Dark matter, gas clouds, the seeds of future stars, all of it operating within a strict cosmic accounting system. Lambda CDM doesn't just predict how galaxies form. It predicts how much raw material was available to form them and when. And according to Boylan-Colchin's analysis, published in Nature Astronomy in 2023, the galaxies Webb was finding were so massive, so early, that building them would have required star formation efficiencies approaching 100%. 100%, every available atom becoming a star, no wasted gas, no failed collapses, no clouds that never ignited, perfect, total, physically implausible conversion of matter into stars on a cosmic scale that has never been observed anywhere in the universe, at any point in its history. Boylan-Colchin described the situation to Science News with a clarity that cut straight through the jargon. We have this reservoir of atoms. Almost every single one of them has to be in stars or in galaxies if these objects are real. That's not a model tweak. That's not a calibration issue. That is a potential violation of the basic rules governing how matter behaves in the early universe. The peer review community took it seriously. Astrobytes, one of the field's most respected research digests, summarized the state of play in February 2024. Webb was reporting stellar masses way larger than what lambda CDM predicts, raising direct questions about the reliability of the existing cosmological model. Not questions about a footnote in the model, questions about its reliability, the whole structure. It's important to note that some of those early mass estimates have since been revised as better spectroscopic data replaced the initial photometric readings. The most extreme claims softened somewhat under scrutiny. That is science working exactly as it should, but the core problem didn't disappear when the numbers were refined. The galaxies were still too big, still too early, still sitting in a universe that, by every prior calculation, shouldn't have been ready for them yet. And that was just the first problem Webb handed us. The galaxy mass problem was jarring enough on its own. Then Webb kept going, layer by layer, across separate research teams working independently on separate questions. The anomalies accumulated, and each one hit a different load-bearing wall of the standard model. The first was the black hole problem. In 2025, using Webb's instruments, astronomers confirmed an actively growing supermassive black hole sitting at the center of a galaxy that existed just 570 million years after the Big Bang. Under every pre-JWST model we had, supermassive black holes were understood to require at least 1 billion years to reach that scale. Fed slowly by infalling matter, growing through a process called accretion that obeys firm physical speed limits. There simply wasn't supposed to be enough time. George Ricci, a University of Arizona astronomer and a pioneer of infrared astronomy, didn't soften his assessment. JWST has shown that our ideas about how supermassive black holes formed were pretty much completely wrong, he said in a December 2025 University of Arizona press release. It looks like the black holes actually get ahead of the galaxies in a lot of cases, not slightly ahead of schedule, not at the edge of what the model permits. Completely wrong. Then came the shape problem. An ASU-led research team, working with collaborators from MIT, Harvard, and Taipei, published findings in Nature Astronomy in 2025 showing that young early universe galaxies observed by Webb display unexpectedly elongated filamentary shapes. This matters because galaxy shape isn't arbitrary. It's a direct fingerprint of the dark matter scaffolding the galaxy formed within, and the shapes Webb is seeing don't match the predictions of cold dark matter, the specific variety of dark matter that lambda CDM is built on. They match far more closely simulations built around warm dark matter or wave dark matter, fundamentally different substances with fundamentally different behaviors. The model isn't just wrong about when galaxies appear. It may be wrong about what the universe is made of. Now set all of that against what we thought we knew before Webb arrived. The Hubble Ultra-Deep Field was, for decades, humanity's deepest view of the early universe, a breathtaking optical image revealing thousands of distant galaxies in a patch of sky smaller than a grain of sand held at arm's length. It was groundbreaking. It was also limited to optical light and shallower cosmic depths, and critically, it showed us a universe that matched our expectations, dark, sparse, slowly assembling its first structures in the distant reaches of time. Webb looks at the same early universe in infrared and sees something else entirely, not a dark, patient cosmos carefully building itself piece by piece. One research paper described what Webb is actually finding as a cosmic rush hour. Vigorous, chemically enriched, structurally complex galaxies appearing 100 to 200 times more frequently than any model predicted in an era when the universe was supposedly still figuring out how to make its first stars. Hubble showed us a sketch. Webb is showing us the painting underneath, and the painting looks nothing like the sketch. Overmassive galaxies, premature black holes, wrong shapes, wrong numbers. Any single one of these anomalies could be debated, refined, or explained away with a careful enough argument. But all four, arriving simultaneously from independent teams using independent methods, that is a different kind of problem altogether. It's easy to hear all of this and file it away as a problem for physicists, something happening in journals and conference rooms that has no bearing on your actual life. But that's not quite right, because the Big Bang model isn't just an academic framework, it is the story of where you came from. Every atom in your body was forged in the nuclear furnace of a star. The carbon in your cells, the iron in your blood, the oxygen moving through your lungs right now. All of it produced across billions of years of stellar life and death in a universe that lambda CDM tells us is 13.8 billion years old, evolving in a specific direction, at a specific rate, toward a specific fate. That model doesn't just describe distant galaxies, it describes the origin of the matter you are made of, and the timeline on which everything that has ever existed came to be. If lambda CDM requires significant revision, and the evidence is mounting that it does, then those numbers are not fixed. The age of the universe could shift. Our understanding of what dark matter actually is could change entirely. The ultimate fate of everything, the long, slow arc of cosmic history that ends in either heat death or something stranger, depends on getting the expansion rate right. And right now, we cannot get it right. Not even close. The Hubble tension is where this becomes impossible to ignore, the two most precise measurements of how fast the universe is expanding, one derived from the early universe, one from the local universe measured directly around us, disagree at greater than 5 sigma confidence. 5 sigma. That is the gold standard for a confirmed physical discovery in particle physics. Applied here, it means the disagreement between these two measurements cannot be explained by instrument error, statistical noise, or bad luck. They are, under any known framework, simply incompatible. A December 2025 status report put it with uncomfortable directness. Expectations that advanced technology would resolve this discrepancy have not been met. Webb was supposed to settle this. Instead, it appears to have deepened it. For the scientists living inside this moment, the feeling is not simple. It is disorienting and electrifying in equal measure. The particular terror of watching something you built your career on develop cracks, combined with the particular thrill of knowing those cracks mean something real is waiting on the other side. Nobel Prize-winning cosmologist James Peebles has framed it as opportunity rather than catastrophe, noting that science thrives on doubt, and he is right. But thriving on doubt requires first being honest about how much of it there currently is. The universe is not smaller than we thought. It is stranger, and strangeness at this scale has consequences. Here is the distinction that almost every headline about this topic gets wrong, and getting it wrong matters. The Big Bang is not under threat. The event itself, the origin of the universe from an extraordinarily hot, dense state approximately 13.8 billion years ago, is supported by multiple independent lines of evidence so robust that no serious cosmologist is questioning it. The cosmic microwave background, the abundance of light elements, the observed expansion of space, these are not ambiguous signals. The Big Bang happened. That is not what Webb is challenging. What Webb is challenging is the specific theoretical architecture we built on top of it. Lambda cold dark matter. Lambda CDM is not the Big Bang. It is a framework constructed to explain how the universe evolved after the Big Bang, how matter clumped, how dark energy drives expansion, how cold dark matter scaffolded the first galaxies into existence. It is the best model we had, and it is the model that Webb's observations are placing under extraordinary pressure. The response from the scientific community has not been denial. It has been exactly what you would hope for, a serious, peer-reviewed search for what comes next. Several candidate frameworks are already on the table. Early dark energy proposes that a brief additional burst of dark energy existed in the early universe, temporarily accelerating structure formation and allowing massive galaxies to assemble faster than cold dark matter alone would permit. Multiple papers published between 2025 and 2026 demonstrate that early dark energy models can match Webb's observed galaxy counts without discarding any core Big Bang physics. And as a bonus, they help narrow the Hubble tension simultaneously. That is not a small thing. That is one proposed solution quietly doing the work of two. Then there is the dark matter question. Rather than the cold, tightly clumping dark matter, lambda CDM assumes warm dark matter or wave dark matter. Substances with smoother distributions and different behaviors produce galaxy shapes in simulation that far more closely match what Webb is actually seeing. Research from ASU, MIT, and Harvard, published in Nature Astronomy in 2025, makes this case directly. A third model, proposed by researcher Rajendra Gupta, stretches cosmic time at high redshifts, giving the early universe more room to build complex structure without requiring physics we've never observed. And yet, lambda CDM is not dead. That phrase is, remarkably, the actual title of a peer-reviewed 2023 paper that reassessed the most extreme galaxy mass claims and found them overstated. Some early estimates are being revised downward as precise spectroscopic measurements replace the initial photometric readings. The field is correcting itself in real time. What Webb has done is not break cosmology. It has broken cosmology open. Come back to MOM-Z14 for a moment. Just sit with what it actually is. A galaxy. Confirmed, peer-reviewed, published in the Open Journal of Astrophysics in January 2026. Its own discoverers described the act of observing it as witnessing a cosmic miracle. Its light left its source 13.5 billion years ago, when the universe was just 2% of its current age. A newborn cosmos that, according to everything we thought we understood, should have been nowhere near ready to produce something like this. And yet NASA's own description of MOM-Z14 pulls no punches. It is brighter, more compact, and more chemically enriched than astronomers expected to find in this early era. It shouldn't be there, and there it is. That tension between what the model predicts and what the universe keeps insisting on showing us is not a failure of science. It is science doing exactly what science does when it is working at its highest level. Consider the parallel. In the 1990s, the Hubble Space Telescope delivered measurements precise enough to build lambda CDM into the dominant cosmological framework it became. Hubble put the model on the pedestal. Now, as one research paper framed it with striking directness, Webb is perhaps playing that same historical role, not confirming the pedestal, but questioning whether it was ever the right one. The instrument that built the standard model has been succeeded by the instrument that may force us to build a better one. And Webb will not be working alone for long. The Nancy Grace Roman Space Telescope is preparing to join the hunt, and together with Webb and the Euclid telescope, this trio may push observations to redshifts of z equals 15 or beyond, deeper into cosmic dawn than any instrument in history has reached, closer to the first light that ever existed. Every answer Webb finds opens 10 new questions. Every record it breaks reveals a universe more active, more structured, and more surprising than the one we thought we were living in. That is not a problem. That is the whole point. Before you go, I want to ask you something, and I mean this as a genuine question, not a rhetorical one. If scientists confirm tomorrow that the universe is actually older than 13.8 billion years, or that dark matter behaves completely differently than we ever assumed, would that change how you see your place in it? Would the ground shift under you even slightly, or does the feeling stay exactly the same either way? Drop your answer in the comments. There is no right response here, and I suspect the people who say yes and the people who say no will have very different reasons. I want to read both. If this video gave you something worth thinking about, the like button and the subscribe are right there, and they genuinely help this channel keep covering the biggest scientific story unfolding in our lifetimes. Because this one is not finished, not even close. We are going to be coming back to dark matter specifically, because what Webb's galaxy-shaped data is quietly suggesting about what dark matter actually is may be the most unsettling piece of this entire puzzle yet. The universe is not smaller or less mysterious than we thought. It is stranger. And we are only just beginning to understand how much. And while you were watching this video, the findings kept coming. Also published in January 2026 in Nature Astronomy, researchers using Webb identified an ongoing collision involving at least 5 galaxies, a complex, violent merger detected just 800 million years after the Big Bang. That alone would be remarkable. But what made it genuinely alarming to the scientists involved was what the collision was spreading: heavy elements. Oxygen and other products of stellar nuclear fusion, already being redistributed between galaxies at a scale and complexity that existing models predicted shouldn't appear for well over 1 billion years. The chemistry of a mature, evolved cosmos showing up in a universe that was supposed to still be in its infancy. It is not one anomaly. It has never been one anomaly. It is a pattern. And consider this final detail. MOM-Z14 displaced its immediate predecessor, JADES-GS-Z14-0, by approximately 10 million years. 10 million years in a universe nearly 14 billion years old. The records are falling in increments so small that astronomers openly acknowledge no title is safe. The frontier is moving, and it is moving fast.